Good afternoon, everybody. The afternoon session. Now we're happy to have David McAllester, who is going to speak about logic-dependent type theory. Thank you.
Thank you. Okay, so you're all familiar with Math Zero. And when I saw this, it was obvious to me to ask the question of whether it would be possible to do for mathematics what was done for chess, Go, and shogi. Math Zero, and many people are interested in this question. And DeepMind recently announced alpha proof, which is certainly an effort in this direction. So what I'm going to do today is not directly address this question, but I'm going to talk basically about the technology underlying Lean. So Lean is the system that many of these efforts, including alpha proof, use as the verifier, the base verifier for mathematics. And Lean is emerging sort of as the dominant system in this role. And it's not, it wouldn't be immediately obvious. 10 years ago, it wouldn't have been obvious why that would happen. There are other systems, MetaMath, Mizar, Isabelle HOL, that are used for verification, but Lean is emerging. And Lean is a dependent type theory. So what I'm going to be arguing is that dependent type theory has these magical properties that are sort of essential for automating mathematics. And Lean, however, is derived from Martin-Löf type theory in 1972, and it was not motivated by the things I'm going to be talking about. Okay, I want to start by pointing out that there are two cultures. Like when you build a system that plays Go or chess, it's very different to be one of the researchers that are building that system from being a person who plays Go or chess, right? So the AI construction community is a different community. And what I have this feeling that the Lean developers are really logicians. And logicians it's a different community from the mathematics community. So I'm a little concerned giving this talk because I think many of you are in the mathematics community, and I'm going to be talking about logic, which I'm not sure everyone's going to be excited about. But this talk is about logic. Okay, what's this advantage that Lean has? So I'm going to start by sort of trying to give you the bottom line, the point I'm trying to make. And that is, I'm going to call this thing the grammatical functor property. And the idea is that in Lean's a type theory. And a type theory has the property that expressions can be well-formed or not. Right? So we're going to have a grammar that determines when the expression is well-formed. And it's going to have the property that if I've got a well-typed, grammatically correct definition of a mapping from one concept to another, that grammatical property is going to guarantee that the mapping is a functor between categories. Every concept is going to be every concept in mathematics is associated with the notion of isomorphism. And if you take the objects of that concept and their isomorphisms, it forms a category called a groupoid. A groupoid is a category where every morphism is an isomorphism. And the idea is that isomorphism is really fundamental to mathematics. And you really need the property that if two things are isomorphic, then any statement about one is true of the other. And what we want, so what I want you to think about is something as complicated as taking a topological manifold and defining its homology group or homotopy group, right? That's a map. And somehow we know, when I took topology, it was explained to me that this gives you a way of classifying the manifolds, right? If you show that they have different homotopy groups, then they're different. Now, for that to make sense, you have to, understand that definition of the homotopy group was well formed. It only used the structure of the manifold. And so what we want is a type system with that property. Now, Mike encouraged me to start slowly, assuming that I have this impression that these days people get a PhD in mathematics and never really have to study logic. So I want to sort of do a gentle transition into thinking about logic. Right, so try to put yourself in the mindset of a lean developer. So I want to start by considering just a simple first order language with zero and successor. And in that language, the first order language, we can write these formulas. So you're all familiar with this notation. The first one says that zero has no predecessor. The second one says that everything that's not zero has a predecessor. And the last one says that nothing has two predecessors. So I can take a universe of objects, a meaning of zero and a meaning of successor, and assign a truth value to all of these expressions, right? So they're going to be truth conditions. And I want to think of this as I want to bring in the concept of grammar, right? So we have the set of well-formed expressions. So in this language, with zero and successor, I've got terms, and a term is sort of trivially defined. It's either a variable, the constant zero, or the successor of a term. And I want you to think of this as being like natural language, right? You say S goes to NP, BP. This is, a term goes to variable zero or successor of a term. And the formulas are also, you can think of them as grammatical language defined by a term. A formula is either an equation between terms, universal, existential, disjunction, conjunction, or negation. Okay, so we've got this language. Now in a first order, I'm going to use the word signature to be the thing, the grammar, the thing that defines a set of grammatical expressions. So in first order logic with one universe of objects, the signature is just the function of predicate symbols and how many arguments each one takes, their arity. And that defines the set of well-formed terms and formulas, right? So the signature is going to define a grammar. We can immediately go to multi-sorted logic, right? So in a vector space, we have vectors and scalars. And these are two sorts, right? Multi-sorted logic goes back to the early days of first order logic. Typically, it's multi-sorted first order logic. So the notion of sort, as in vectors, as in scalar or vector, is going to be central to this notion of isomorphism. And we can immediately go to higher order multi-sorted logic. So I'm first going to define a system of types. So let me go back here and say, in a multi-sorted logic, I'm going to switch to introducing a set of terms of the language. So this would be like the scalar vector product. And for each term of the language, it's going to have a type. And that's what's going to define the signature, right? So I've got this set of sorts. And there's a question of what is the set of types? So we're going to introduce a signature by assigning a type to a set of constants of the language. The types are naturally something called simple types. So a simple type is either one of your sorts, so vector or scalar. We're going to have the type bool. This is the type of all pairs of, so if I could say vector cross scalar, and that would be a type of pairs. But that can be any type, and I'm going to have an arrow space, a space of functions between types. Is this all making sense? So in a topological space, I have an open predicate which is going to take a set of points, a function which I can think of as a function from point to bool, and it's going to give me a bool. And that defines the signature of a topological space. It's open sets. It's open predicate. I get the feeling that from this morning that this is a somewhat combative or interactive audience. And don't let me get away with anything. I welcome interaction. Question.
So should I interpret that as meaning the open sets to which a point belongs? That's point, arrow, bool.
So open is a function that's going to take a set to a truth value.
Okay, and if the set is open, the truth value is 1 or something.
Right. Exactly.
But It only responds to sets that contain the point in question. Is that why it's point arrow bool?
Function.
No, it's not, it's
Bool
defined
is a
as
subset.
membership function.
I'm using point arrow bool as a way of representing a set.
Subset of set.
So the membership function is that point is a set, which goes to specifying the set.
Okay.
What is the double colon?
Oh, it's just the way I write the grammar. I use a double colon if I'm using something called Bacchus normal form for writing grammars. Okay, and so now we're in higher, if I use
Sorry,
simple.
can I ask one more elementary question? Sort has two English meanings. Which one am I supposed to be thinking of here? Like a sort is a type, but it's also a verb to sort things.
Type.
Okay,
And it has a very special meaning as a type,
Okay.
because it's going to be the foundation of isomorphism. So the word sort is very important here. So this, once I say I've got simple types, I'm in higher order logic. I'm no longer in first order logic. Once I start assigning constants to, like this open thing is something that's taking a predicate as an argument. That's the definition of something that's not allowed in first order logic, right? That's higher order logic. And these simple types give me, a very natural and simple higher order formalism. So if you hear Isabel HOL, that HOL is referring to simple types. And using these simple types, I can write the induction principle for the natural numbers. I meant to point out when we did that first set of properties of the natural numbers, it doesn't pin down the natural numbers. You need an induction axiom. It pins, you get everything that's accessible from zero, but you can have an infinite chain in both directions. It's not accessible from zero. So to rule that out, you need this induction axiom. Now, so this is saying for all predicates, n arrow bool, and then it's the induction axiom. If the predicate is true of zero and true of x implies true of successor x, then it's true of everything. Standard. Now, normally in piano arithmetic, this is done with a first order schema, which makes the inference system enumerable. Here, I'm going to make a big point later on about defining things semantically. When is this true? I said that these formulas have truth conditions. When you look at those formulas, you have a model, you can assign a truth condition to the formulas. This thing is going to be true if and only if you're actually talking about the natural numbers. And that's a little tricky. If there are any questions about that, but I'm focusing on truth. If it's really true that for all predicates, then the only model is the natural numbers. Okay, so now we're going to be doing type theory. So in type theory, we keep making the language more elaborate. So the first step we're going to be doing is sort of moving in the direction of programming languages. So I had this grammar for terms, right? I said a term is either, a variable, zero, or successor of a term. If you have multiple sorts, each sort can be thought of as having a grammar, all the terms that type as that sort. Now we're going to extend the set of terms with a pairing construction and projection functions. So for any signature, for any set of constants of my language that I'm going to define terms over, I'm going to extend it with pairs and projection. I'm also going to introduce notation for functions. So this lambda, how many people are programmers and have seen lambda? Okay. Good. So I can extend it with lambda and we can well type lambda expressions. And it's again, I want to emphasize being semantic. And so I'm giving a semantic definition of these notations. Okay, signature axiom classes. I recently went to the Wikipedia page on the notion of a structure. And it was very sort of non-committal. Bourbaki gave a definition of structure in 1939. But the definition of structure seems to be most appropriately approached in terms of logic, in terms of this grammatical signature defining a class of objects. So once you have a signature, you typically add axioms. So a group is defined by the group operation, the identity element, the inverse operation, and conditions. So you define a concept with a signature and axioms. So you get a signature axiom condition. And any signature axiom class, so we're using type theory sort of as a foundation for mathematics. Any signature axiom class defined this way by a signature and axioms defines a groupoid. It gives you a notion of isomorphism between the objects, right? So an isomorphism between the objects is bijection. I have two objects in this class. They both interpret the same sorts. They're going to be isomorphic if there's a mapping, a bijection between sort A here and sort A there and sort B here and sort B there. A bijection between the sorts that carries the data of one. What do I mean by the data? I mean the interpretation of the symbols of the language. So for example, a topological space interprets the symbol open. A group interprets the symbol group operation, identity function, identity element, and inverse function. So the data, when mathematicians talk about data, I think the right way to interpret that is they're talking about the interpretations of the symbols of some signature. And two structures of the same signature are isomorphic if there exists a bijection between their sorts that carries their data. And the data is defined by simple types, and it's not difficult to define carrying values of simple types, or by induction on the type.
Why do you want the same source? You have two signature axioms. They all have a certain set of sorts. Everything. Why the sorts be the same?
So I'm defining isomorphism.
Yes, but they could be isomorphic, have the same structure, but the sorts are many different.
Let me come back to, I'm going to come to a notion of cryptomorphism, and cryptomorphism covers that issue. So ask it again when we get to cryptomorphism.
So you talk about bijection. Why do these things have the sets? I would forget the sets. I mean, there are mathematical objects where bijection is not really the right notion, right?
Well, I'm being sort of a little basic and simple. Certainly, most of the things I've encountered as mathematical concepts it's appropriate to think of it as a bijection. You go to category. I mean, a category is more abstract, right? If I talk about a class like this, the isomorphisms are bijections. A category is defined in such a way that the isomorphism is just an object and it's just a thing in the category, right? I mean, actually, object and morphism are terms in the language of category theory that define isomorphism between categories. Okay, so now we have groupoid classes.
You go back to the model.
Yeah.
So far, you've described language to express expressions that are well formed. And then you decide, I'm going to have some signature and some actions on one side, another set of signature and actions on the other side. And I want to define the morphism between them.
So what I've done now is said I've got signature and axioms, and I've got different objects that are all instances of the signature that satisfy the axioms.
Objects.
So
What do you call object? You haven't defined object.
So it's in terms of first order logic, it would be the model, right? So the model is going to be an interpretation of each sort as a set, and an interpretation of each symbol of the language, like the operations of a group or the open predicate, an interpretation.
You're introducing a model.
A model.
Because it wasn't there in the talks of model. Yeah. Okay. Understand.
So it's not just about formal expression. At this point, you got something that says true or false, which is a model, right?
So given a model,
Yeah.
every formula gets a truth value.
So the model comes with evaluation which give the true value, something like that. Or is
So the model just consists, so a group would be a model, a particular group. But we have the class of all groups. Right, and the class of all groups has this notion of isomorphic group. And so the class of all groups is the thing that is the groupoid. But the group is the model. And given a model, every formula has a truth value in that model. Okay, so now so what I've done now is I've sort of defined a notion of structure. Go back to, Bourbaki was trying to define a notion of structure. I've defined a notion of structure in such a way that it's really going through the notion of class, right? A signature axiom class is a collection of objects, and those objects have a well-defined notion of isomorphism. So we now have groupoid classes, these signature axiom classes, but we don't yet have functors. Right, what do I mean by a functor? I mean a mapping between, the mapping from a manifold to its homotopy group, or the mapping from a graph to its graph Laplacian. And these functors can be very complex. That map from a manifold to its homotopy group is complicated. The map from a graph to the graph Laplacian is complicated. And so there's lots of language that gets used in defining that function, and we want to make sure that that language has the property that the mapping we define is a functor. It carries not only the objects, but the morphisms. So if I have isomorphic inputs, I get isomorphic outputs. Okay, so let's get back to this lean's advantage, just to point out, this is the point, right? This is why lean, I think, this is my opinion on why lean is the dominant system. It's because it fits well with the natural structure of mathematics, right? The natural structure of mathematics is this signature axiom structure. And lean has this property that if I've got a mapping between classes and two inputs are isomorphic at the input type, and I apply my functor, they're isomorphic at the output type. And that's something that's just in the structure of mathematics, and the mathematicians really need it. And in lean, there are these macros that implement this property.
Are you distinguishing lean from cock, or would you also treat your cock?
So this property was proved even before there was Koch. There was Martin-Löf type theory, and this property holds for Martin-Löf type theory and is inherited by Koch and lean. Now, I have always been very uncomfortable with constructive logic. Right, I get very angry at people who insist on denying the excluded middle. I'm like, oh, it's true. And so I've always wanted to purge constructivism from the type theoretic foundations of mathematics. So that's what I'm going to do now. But first of all, I just want to point out how central this is to mathematics. Right? If I talk about classification problems, right, you've got a concept, you want to classify it, right? You want to classify the structure, the objects in that class, right? You're only going to classify it up to isomorphism. So the whole classification problem is defined by the notion of isomorphism within that class. And classification, I think, is we're going to talk about this afternoon about automating mathematics and mathematical significance. Classification is a central problem as an outsider, as an AI person. It seems like to me, classification is one of the central issues in mathematics. You define a concept, you want to know what are the objects in that concept, classify them. Representation. Mathematicians always talk about representations. They know what they mean by isomorphism. They know what they mean by classification. They know what they mean by representation. I'm not saying anything the mathematicians don't know. The only thing I'm saying is, how do they know it? Right? This instinctual understanding of classification up to isomorphism, this instinctual understanding of representation, right? You can represent a group as a set of permutations or linear operators on a vector space. What's the difference between the group structure and the representation? Mathematicians understand it. But if you're going to build a system, if you're going to be a lean developer, you have to understand it at the level of the grammar of your expressions that you're building into your language. So a representation is, I mean, we know what a representation is, right? It's adding structure under the sorts, right? So the group has a sort, which is the group elements. A permutation group says the group elements are actually permutations, right? So you're assigning structure under a sort, and that's a representation. Cryptomorphism. So if I take a group, right? A group has, there's different ways of formulating a group. And when you teach groups, you teach that there's two ways to formulate it. You can take just the group operation, and then in your axioms, you can say that the identity element and the inverse operation exist, right? And so you can formulate it just in terms of the group operation. You can also formulate it almost more naturally by saying, well, the data is the group element, the identity element, and the inverse operation. Those are not isomorphic. This gets back to this issue of, it's different structure, it's different data. But there's some sense in which you've defined the same thing. What's the sense in which you've defined the same thing? So this is the term cryptomorphism. And this was introduced was coined by Berkhoff in '67. And I'm taking it here to have a very simple definition. Two objects are or two classes, rather, two of these classes are cryptomorphic. If I can define a functor from one to the other and an inverse functor that goes back, such that if I compose them, I get the identity. So in regards to different names of the sorts, right? If I had two structures that were identical, I could map one to the other. Symmetry. I mean, symmetry is just an isomorphism of an object with itself, right? That's a symmetry. So symmetry is another thing that is understood through this notion of isomorphism. So the point I'm trying to make now is we need to support isomorphism in the foundation we're using.
Sorry, I didn't understand how the definition of cryptomorphism was different from isomorphism. Looked like the definition of isomorphism.
So cryptomorphism is a functor between classes. Isomorphism is a relationship between two objects of the same class. The isomorphism is a mapping is bijections between the sorts. Whereas a cryptomorphism is taking an object and changing its data to be a different set of constants.
So, why groupoid? I mean, usually we talk about functors. So is it that this map only preserves isomorphism? Sometimes when there are maps that are not isomorphic.
So dependent type theory, the thing that it supports is isomorphism and groupoids. It's natural to talk about homomorphisms and algebraic categories or continuous maps and topologies. But isomorphism is the thing that Lean is supporting. I mean, you can define quotient structures. Okay. So this grammatical functor property, what I'm calling this grammatical functor property, was proved from Martin-Loff type theory, from which Lean is derived, by Hoffman and Stryker in 1995. But Martin-Loff type theory goes back to 1972, right? And it was developed by Martin-Loff because of this constructive philosophy. It's the descendant of Brouwer and Heiting, and it's constructivism. And they developed a type theory to embody the constructive philosophy of mathematics. And it's a very strong type theory, and it happens to have this property, this grammatical functor property. So I'm going to argue now that that the constructive philosophy is just a red herring. You can get rid of the constructive philosophy and you can still have this property. And I can't help but, okay, so this talk is very different from one you would hear from a Lean developer, someone in the type theory community. They're going to tell you a story like this. And I'm going to ask you whether this story feels right. So the story you're going to hear is that First of all, constructive logics are based on computer programming. If you talk to somebody in that, the real ardent philosophical devotees will say the only thing that's really there is the lambda calculus. The lambda calculus is a set of programs, right? And it's a formulation of types for a typed lambda calculus, and proof checking is reduced to type checking. A proof of a proposition P is taken to be a well-typed program whose type is P. So to be a constructive proof is to give a program. Yeah.
It might help to give one example. So like what I consider the illustrative example is that the proof that A applies B is a program that accepts a proof of A and gives you a proof of B. So that's like an example of turning logic into programming.
And proofs, propositions as proofs, propositions as types rather. So so you'll hear this proposition as type formulation of the type theory. And then you have to, in order to support mathematics in lean, you have to extend this with the excluded middle and the axiom of choice, because that's what mathematicians use. You have to please your users.
I have a question. When you define isomorphisms, you introduce models. If you have models, you have to exclude the meaning, right?
Yes, right. So I'm doing something different from this.
Okay.
I'm taking a semantic approach, right? And I'll say a little bit more about that.
But you should say, Lane, you can accept, you can use excluded middle as an axiom.
Right, yes. You can add that.
It's not like you can't do it.
It's not like you can't do it. Lean has it, it's just not in the fundamental logic.
Can you say a little bit more about how you get propositions as types? I mean, before you had these simple types, the sorts, and you could take ordered pairs of them and functions between them, and those were, types. How did propositions become types?
So I'm not going to do this,
Okay,
right? In the logic I'm developing, this is irrelevant.
We have some time to discuss after the talk, so maybe we'll try to discuss after.
Yeah,
It's an excellent question, but maybe you don't even have time to probably.
Okay.
yeah. I mean, another example, to use another example, if I want to prove for all x, p of x, I write a program that takes an x as an input and produces a proof of p of x as an output. Just to give another example. Okay, so what I've done here is a semantic approach. So this is following Tarski. And first order predicate calculus has a long tradition of model theory, right? The model theory of first order predicate calculus is semantically based. And there are theorems like the compactness theorem of first order logic that have both a proof that works on proof rules, syntactic proof, and a purely semantic proof in terms of the models of the theorem. And for me, I find the semantic definition much easier. Like, I don't think I did anything in those first slides that was terribly difficult. Right? The idea that you have this data, the data gives you the meaning of the symbols of the language, and then every expression, every term can be assigned a meaning in terms of the data just by a recursive definition. So for me, this is much more natural. More importantly, if you define the language semantically, I'll come back to this. There's an important point I want to make later. Okay, but the language I'm defining is not constructive type theory, right? I'm taking this generalization of first order logic. I'm taking a generalization of the model theory of first order logic, and that's going to define my logic. How do I get to functors? I have not yet gotten to functors, right? I have not yet said how we're going to define this map from the manifold to its homotopy group, or from the graph to its spectrum. So what we're going to do is we're going to make the sorts. So when I defined a class, I said you have these sorts and you have constants of the language, which are defined by simple types over the sorts. Now what I'm going to do is introduce first class sorts. So in a programming language, something's first class if you can put it inside a data structure, or you can pass it as an argument to a procedure. So now I'm going to take the sorts, which are the foundation of isomorphism. The sorts are the foundation of isomorphism. The isomorphisms are the bijections between the sorts, and I'm going to make them first class. And that is the transition to dependent type theory, is first class sorts. So what we're going to do is we're going to introduce set. This would really make a type theorist mad. We're going to introduce set as a type. Okay, so I can declare a variable, a part of the data of an object, to be a set. And that's declaring it to be a sort, because I haven't said anything about what's in the structure of that set. It could be a set of points. Matter of fact, you typically want to think of it as a set of points. Right? A topological space has structureless points. And even in other things like a group, the structure comes from the operations. The group elements are just points. Okay, and then we generalize this pair type, right? This is the type of pairs of a sigma and a tau. We generalize it to a dependent pair type. So the dependent pair type is going to have a first component, which is of type sigma, and a second component whose type depends on the value of the first component. So, example, a magma. A magma is an object that's a pair of a set. Its sort, we're putting the sort in the object, right? It's a pair of a sort and a binary operation on that sort. And that's what this notation means. The pair of a set, and note that the type of the second component of the pair is defined in terms of the sort. Right, so it's a pair. So now we're going to have an object, like if we're defining a signature axiom class, it's going to be a tuple with some sorts and then some operations over those sorts. Right, so the sorts are becoming first class. We can also pass a sort to a function. So I can have a function. Cons here is a list builder. So if you're an old Lisp programmer, cons takes two things and returns a pair. But here I'm thinking of it as a list. I'm thinking of a type of lists. Now, it's convenient to have a list type over any other type. So I can have a list of integers, I can have a list of reals, I can have a list of vectors. How do I have one programming element that covers lists of integers, lists of reals, lists of vectors? Well, I have a general function cons that first takes the type that the list elements are in, and then takes an element and a list and returns a new list that appends this element to that list. So this is polymorphism. If you've heard that phrase, like the programming language ML is polymorphic. What that means is they support this kind of, this form of function. It's also something called system F that supports this. But I'm most interested in this idea that we can put sorts inside of objects. Now I've talked about signature axiom classes. So the next thing I want to introduce is a primitive for stating the axioms, right? This magma had no axioms.
Okay, other question. Notation. Sometimes there was sigma and pi for it.
So this is sigma is a pair type. It's a generalization of cross. Pi is a generalization of arrow. It's the analogous generalization of arrow. So this is going to be the type of functions that takes an x as input in sigma and produces something in a type where the type depends on the value of the input.
Are functions special cases of pairs?
No, not in this system.
What's in front of that was the answer.
Okay, axioms. So I said we started before by saying we have these signature axiom classes. It really forms the classes that I'm thinking about. And we want a type group, right? So how do we define the type group? So I'm going to say, well, a group is a pair of a set, and what I'm going to do is introduce a new type constructor, which takes an element of this function space and says it must satisfy some formula. So this S says, so the general form of S is the set of X in T such that this axiom holds of X. Right, so that lets me put in the group axioms, the statements about the group that I want to hold. And that's, and okay, I see a lot of frowns. You have this, let me back up. You have signature axiom classes, right? So signature axiom class, you define the signature. What's the data? Right, the signature defines the data. And then the data has properties that it has to satisfy. Right, so what I'm trying to do is define the language, of a given class didn't have first class sorts. Right, it was just defined in terms of the symbols that were whose types were defined in terms of the sorts. But that language doesn't, the data is just the symbols defined in terms of the sorts. Now we want the sorts to be part of the data. A group includes its set of group elements as part of its data. So a group is a pair of a set, which is the group elements, and let's say the group operation. So I just wanted to do the group operation. But it has to satisfy the group axioms, the conditions that groups have to satisfy. So that's what this S does. It says, I want an F satisfying axioms. And the axioms can be taken in terms of the sort. So it can quantify over the sort and use make statements about these things. Okay, I'm going to make your life, this slide should really be confusing, unfortunately. I just want to say,
Quick question.
yeah.
You keep the difference between sigma pi pair function. You could have decided, well, I'm going to use the same symbol, flatten everything at that level.
Oh, I see.
Full level hierarchy.
Functions are not here viewed as sets of pairs. Is that the confusion? Is that the issue?
They're different. You could have made a pair be a function.
Sigma is denoting a set of pairs.
Like it's
Pi is denoting a set of functions.
also.
Now set of
Okay, and so now we have three things. We have sigma, pi, and this S, which I'm calling some such that. S is giving me this some such that type. So what's confusing now is the relationship between this and constructive type theory. So I'm going to point out how this is done, how constructive type theory handles axioms. Okay, how does lean in its foundational logic deal with, does it have this signature axiom distinction? Technically, formally in the foundation, lean does not make signature axiom distinction. So the way lean represents group is it represents it as a pair of a set and a pair of a function and a proof that the axioms are satisfied. So we're taking a proof of axiom satisfaction as part of the data of the group. And that's just a different way to do it. And they can sort of make it work, but it feels very unnatural.
How do you do it?
So for me, the data of the group is still what we normally think of as the data. And and I just treat this semantically. I just say semantically, this denotes the set of XP such that this is true.
You verify types.
Good question. And what happens to verification if you use this some such then? I'll get to that. I just want to point out that in most programming languages, there is a distinction between the type system and what's typically called assertions. So in a programming language, if you are really worried about bugs that the type checker isn't going to catch, right? Some programming invariant that's true in a certain line of code. I know that this line of code, P is a prime number. And I want to check that, or P is an even number. So most programming languages support this notion of making an assertion is checked at runtime. And those assertions typically check program invariants, and program invariants are undecidable. Right? It's actually undecidable whether a number is even at every point in a program. I just point out that programming languages make this distinction between what I'm calling axioms and what I'm calling the signature. And programming language people will talk about the signature of your function. What are its input types and what is its output type? So the functions have the signature, but we also have these assertions that are going to be checked at runtime. I'm personally building a competitor to lean. Lean, we should have a healthy environment. Lean should have a competitor. So I'm building a competitor to lean. Whether this works, if it has any advantage, it's going to be in the level of automation. I don't know if it's going to work, but I need something to do in my elder years. Okay, I mentioned this to people in the lean community, and they said, you can't do that, that's undecidable. You can't have a certain, types with an arbitrary formula that has to be satisfied, that's undecidable. You can't put that in the type system. I did. And I've gotten it to work, I believe. In Alfred, there's signature checking. And signature checking is decidable. If the signature checking fails, your program is wrong. Your expressions are, I should say your statements, your mathematical statements are wrong. They're poorly typed. Axiom checking is undecidable. So what do you do? Well, suppose I've got a function that wants to take a group. And I've got some representation of something that I think might be a group, but I'm not sure, or at least the system isn't sure. And suppose the system says, oh, you're passing a function to a group and I can't prove it's a group. So the idea is you just have a fast, incomplete decision procedure for whether it can tell that the system is a group. And if you make that strong enough, a lot of these, things will just go through. If it can't do it, what you do is you back up and you say, well, I'll prove that it's a group. And you want to have the property that if you prove it's a group, then the axiom checker will say, yes, now it checks.
Where does that fit in your framework? So we want to give a point.
Well, I haven't talked about the language of proofs.
No, but just accepting that proof is a thing, and then like the framework, there has to be a slot, and I say, here's my proof.
No, I don't. There's no slot in the data structure that is.
So what do I say?
Suppose I've got some data, I've got a set and a group operation. Like suppose I define, a set of permutations that's closed under composition. That either is or is not a group, right? Semantically. So I can prove that it is, if it is.
Those proof is complicated.
I can write a long proof.
Someplace in the application, but it's not.
Well, this system's going to be like lean in the sense that you state things and prove them.
Okay, yeah, I'll ask you that.
Okay.
So what if I gave it something that's undecidable?
So what do you mean? You mean independent? So there are, by Gödel's incompleteness theorem, there are things that are true which are not provable, even in ZFC.
That's what it is.
Right. So if it's independent, you're stuck.
It's like,
You can make it an axiom
But why?
if you want to.
You could make it a supposition. Right. You could say, well, suppose it's true.
but that would be adding another. That would, in this case, I would be adding another type too.
No, you would just say, you set up an implication. You would say, do inaccessible cardinals exist? Which is sort of independent of ZFC, unless you assume it. So you could say, well, I'll assume inaccessible cardinals exist. Or the existence of inaccessible cardinals implies. So you don't need to extend the way, you just set up a supposition or, implication.
That would go into S.
If a function wants, if I defined a function that took as an argument an inaccessible cardinal, that application function to a term would be well typed in some contexts where I've made the right assumptions and not well typed in other contexts where I haven't made that assumption. Okay, I just said this. Variance of dependent type theory. This is where, I mean, these systems are a lot like programming languages, and I didn't really appreciate that until fairly recently. It's not enough to just specify a type system with the groupoid, with the grammatical functor property, and it's ZFC complete, right? That's another condition you want. You want to be able to prove anything that's a theorem of ZFC. So you want a type system that supports the grammatical functor property and is ZFC complete. But even with those constraints, different languages are going to be significantly different. What features you support, just like programming, right? Object-oriented programming is friendlier than languages that don't have it, even though they're both Turing complete. And I'm particularly interested in object-orientedness because mathematics seems to be very object-oriented, right? I mean, these objects we're talking about are analogous to objects in object-oriented programming. Okay, I want to go back to, I think I should have brought this up at the point I was talking about semantics. If we think about building one of these systems, the way that the type theory community works is they define this very tight, very, in some sense, minimalist, really, really small set of inference rules, type inference rules. And then they're going to reduce everything to that. But they're thinking, I find them to really think syntactically. If you define things semantically, for me, as an implementer, all I have to do is guarantee that everything I do is sound. And I understand the semantics and I understand what soundness means. And then I'm free to write algorithms, to write inference rules, to write whatever code I want, as long as I can prove to myself that it's sound. Whatever rules I want. Okay, some speculation. I'm an AI person. I like to think about AI questions. So the question now is, you know, it's strange to me that, not strange, it seems to me that human mathematicians have this wired into their cognitive architecture. They somehow understand what it means to be a meaningful, grammatically correct statement of mathematics. So can we interpret dependent type theory as a theory of some kind of human cognitive grammar? Is it an AI theory? Is it a theory of thought? Speculation. Here's another speculation. I really like this object-orientedness. So it's everywhere in programming. Right? We have objects, we have classes, we have methods. Mathematics is object-oriented in the sense of these objects that we've been talking about I've been talking about objects and classes, right? This whole talk has been about objects and classes. So object orientation is central to mathematics. Now, it turns out that the semantics of natural language in general, you know, we have concepts, types, and then we have instances. I have the concept of giving, and then I have an instance of that action of giving. And those instances have roles. So there's this FrameNet FrameNet project that's been going since '76, which is sort of formulating the semantics of natural language in terms of frame structures, which are a lot like objects. So I have to think that this is important. And so the question is there some descendant of the transformer that builds this into the architecture? Now that's a real speculation. I really think there's something about object orientedness that matters. All right, here's one for Mike. What is an electron? This is real speculation. I talked about cryptomorphism. Right, so cryptomorphism says that they're the same object. You can represent intuitively the same object as different data. Right, a group can have just the group operation, or it can have all the operations. They're different not different representations. They're different structures that are sort of convertible between them, that represent the same data. We mathematicians have this notion of being the same data, whatever that means, right? Two definitions are giving you the same data. And that means you can map the data in this form to the data in that form. So if we ask what really is the object, if I give you a mathematical object and ask it, what is it really? It's not really a meaningful question, because the different ways of formulating it are giving you the same data. And it's really sort of that data that is the object, right? And the one thing that data has that's preserved under all of these ways of converting it to cryptomorphic equivalence is the symmetry group, right? They're all going to have the same symmetry group on the same sorts. So maybe that's why we can't talk about what an electron is beyond its symmetry group. But that's real. I mean, I'm not a physicist. I'm treading on strange ice. So this is my summary. This is the grammatical functor property. And the claim is that a foundational system needs this property. It's fundamental to mathematics. It's their independent type theory. Constructivism is irrelevant. So